So this is the 18th video on friction. In this video also I'll take up a numerical problem on friction. Okay. First what I'll do, I'll write down the problem. Okay. The problem is this. A small block of mass m, a small block is placed over a rough horizontal surface. Over a rough horizontal surface. And the block is initially at rest. The friction coefficient between block and the surface is mu. Find the minimum force to be applied to the block so as to cause it to slip, and also the direction which this force makes with the horizontal, and also which the direction which this force makes with the horizontal. So two things we have to determine. Okay, all right. इसको पूरा मिटा देते हैं. ठीक है. First I'll draw the diagram of the situation and then I'll solve the problem. Okay. First, I'll draw the diagram of the situation. Solution SOLN. This is a rough horizontal surface. A small block of mass m is placed here. Friction coefficient between the block and the surface is mu. Now, it is required to apply a minimum force on this block so as to cause the block to slip over the surface. Now we have to determine that minimum value of force and also which the direction of this force which makes with the horizontal. These two things we have to determine. कि दो चीज़ों को पता करना है. तो सबसे पहले देखिए क्या करना क्या है इसमें कि हम इसका फ्री बॉडी बनाएंगे, ब्लॉक का फ्री बॉडी डायग्राम ग्राउंड फ्रेम में. ओके. एक तो उस पर एक वेट लगेगा mg वर्टिकली डाउनवर्ड. ग्राउंड इज नॉर्मल फोर्स n लगाएगा अपवर्ड डायरेक्शन में. अच्छा, हम लोग को मिनिमम फोर्स बताना है जिसके लिए ब्लॉक इस पर स्लिप करे सरफेस पर. मिनिमम फोर्स व्हिच वी हैव टू अप्लाई. नाउ सी, सपोज दिस फोर्स इज बीइंग अप्लाइड एट दिस पॉइंट, मटेरियल पॉइंट ऑफ द ब्लॉक. ओके. देखिए, अगर मिनिमम फोर्स से ब्लॉक को स्लिप कराना है, डायरेक्शन ऑफ फोर्स which is to be applied to this block should make some acute angle theta with the rightward horizontal through the point of its application. This is the point of application of given force. This is the rightward horizontal through this point of application. In order to cause the block to slip over the surface by minimum force, this minimum force should be directed something like this, along this direction. Okay. This force makes some angle theta. Okay. We have to determine this theta and minimum value of this force. Now one more thing, component of this force in rightward direction will be F cos theta. This component will cause the block to slip over the surface. So because of this F cos theta component, there is a tendency for slip of the block over the surface. So the ground will exert a friction force F in the direction opposite to the direction of relative slip. Okay, fine. Now see, for no slip of block over the surface, for no slip, and no slip, NS meaning no slip of the block, what should be done? F should just be equal to F cos theta. I hope it is clear. अगर small f cos theta के बराबर है तो slip नहीं करेगा ये. But we know from the property of friction that F is bounded by the quantity mu n, where mu is the coefficient of friction between the block and the surface, n is the normal force on the block due to surface, and more than equal to 0. F is equal to F cos theta. So F cos theta is less than equal to mu n. So long as this inequality is satisfied, the block will not slip over the surface. This means that if the block has to slip over the surface, then F cos theta should exceed mu n. This is what is the meaning of this equation, inequality. So in order to cause the block to just slip over the surface, what condition should we hold? F cos theta should exceed mu n. Now mu n is the limiting force of static friction between the block and the surface. So in order to cause the block to slip over the surface, component of applied force F in rightward direction should just exceed the limiting force of friction between the block and the surface. This is the required condition for the block to cause to slip over the surface. Okay. So I'll write this inequality here. So this inequality I'll write here. Okay. F cos theta is less than more than equal to what? Mu n. Alright, fine. Now I have that side. Now we have to find the value of n. Now the block is in vertical equilibrium. In vertical direction it has no movement at all. That is, acceleration of block in vertical direction is 0. So net force on the block in vertical direction is 0. So this means total upward force on the block is equal to total downward force on the block. Now from this FBD we can see that total upward force on the block is n plus f sine theta. N plus f sine theta. That is equal to total downward force on the block, which is simply mg. So n becomes mg minus f sine theta. So this n is substitute in this inequality. F cos theta is more than mu times n minus f sine theta. Now this f I bring in left side of the inequality. F becomes common. Cos theta plus mu sine theta is more than mu mg. F is more than mu mg by cos theta plus mu sine theta. So if the applied force makes an angle of theta with the rightward horizontal, then in order to cause the block to slip over the surface, F should exceed this value. Okay. So let us denote this by F naught. So F should exceed this quantity for a given applied force in a direction making an angle of theta with the rightward horizontal. Alright. So that is equal to F should exceed this F naught. Alright. Now for every value of theta there is a value of F naught. Now we have to find the minimum force F. The value of theta should be such that this F naught is itself minimized. Okay. Now rub this one. So for each value of theta we get a value of F naught. Now theta should be chosen in such a way that this F naught is itself minimum. Okay. So for F naught to be minimum, dF naught by d theta should be 0. Okay. Or we can say in other way also, if F naught is minimum, this implies that cos theta plus mu sin theta is maximum, because numerator is constant mu mg. So F naught to be minimum, cos theta plus mu sin theta should be maximum. This means d by d theta of, from the rule of calculus, cos theta plus mu sin theta should be 0. Now d by d theta of cos theta is minus sin theta, and d by d theta of sin theta is cos theta, is 0. Alright. I'll rub this one. Alright. So I solve this equation. So sin theta I take it to other side, or I write this equation this way. Sin theta is equal to mu cos theta. Sin theta by cos theta becomes tan theta. Tan theta becomes mu. Okay. So this, at this value of theta, applied force will be minimum. So this means theta is just tan inverse mu. So in order for the force F naught to be minimum, theta should be at this angle. This is the first part of the answer. Answer to first part of the question. Okay. Now we have to determine the minimum value of this applied force. So I substitute this value of theta in this equation, inequality, then I get the value of minimum force. Alright. Now tan theta is mu, so we need cos theta and sin theta. From trigonometry it follows that sin theta is mu by root under mu square plus 1, and cos theta becomes 1 by root mu square plus 1 from trigonometry. I hope it is clear. Fine. I rub this first column. So this cos theta sin theta is substituting this inequality. So minimum value of the force is this. Cos theta, that is 1 by root mu square plus 1 plus mu sin theta, mu, and sin theta is mu by root mu square plus 1. This becomes mu mg, this becomes mu square plus 1 by root under mu square plus 1. So this becomes mu mg by root under mu square plus 1 is the required answer. Okay. So minimum force to be applied to the block should be mu mg by root mu square plus 1, and this force should be applied at an angle of theta with the rightward horizontal to the point of projection. The tan theta is mu, that is theta is equal to tan inverse mu. Okay. Tan theta is equal to mu, that is theta is equal to tan inverse mu. Okay. So this problem I have fully solved it. I hope it is fully clear to you. Okay. You go through it carefully. In case you have any doubt, you write it in the comment box. I'll explain it. Okay. So I'll close this here. Next video also I'll take another similar problem, but a variant of this problem. Okay. That will be a generalized form of that problem, which I'll discuss in the next video. Okay. So I close it here. Fine.